Mr. Chairman, dear colleagues, my name is Krasimira Stoilova. I work in Institute of Information and Communication Technologies to Bulgarian Academy of Sciences. And the study is titled Optimization Models for Urban Traffic Management. And this is the content of the presentation. The urban traffic in city areas leads to serious problems with traffic jams, noise pollution, social problems, etc. And the most widely used management method is through the setting of traffic lights at intersections. The goal of the study is to derive control models for reducing the vehicle queues in front of traffic lights to achieve bigger outflow compared to the inflow of cars at each intersection of a given network, and to insert more constraints in the optimization model in order to reflect more conditions near to the real dynamics. To achieve this goal, it is necessary to solve several tasks, to choose an appropriate method for formalizing traffic management, to define the corresponding optimization problems, to make numerical simulations, and to compare the proposed models with the existing similar ones. Wide use method for traffic control modeling is traffic light settings on the base of so-called store and forward model. This model says the number of vehicles at given moment is equal to the number of vehicles at previous moment plus incoming vehicles minus outgoing vehicles. The outcoming of the crossroad section vehicles depends on green line duration U and capacity of the street S. And if the control cycle is K, then this equation, this model is simplified to number 3. In our approach, we complicated this store and forward model because we want the outflow to be bigger than the inflow, and this equality becomes inequality. Here it is reflected, this requirement. The first management optimization model is a nonlinear quadratic optimization model, which minimizes the queues in front of intersections and green light durations. This is in quadratic form. When the green line, red line, and yellow line is their sum is the cycle duration, y. The control variables x and u are limited to boundaries. Later, this model is denoted as deterministic problem. The topology of the network consists of 4 crossroads. The traffic is, the number of vehicles is denoted by X. We have 16 traffic flows. The capacity of the streets are denoted by S. We know them, and we have to determine the green light durations of these 4 intersections of the network in a manner that the queue lengths in the network to be less. The next model which we propose is so-called stochastic optimization model, because the character of traffic moving has a stochastic nature. This uh, stochastic behavior of the traffic we formalize in store and forward model by adding one component epsilon, which reflects this stochastic moving of the traffic. The number of vehicles at a given section is a random variable, and we put the requirement that the probability this value to be higher than its maximum must be lower than value of alpha. P, this is a probability density functions, and value of alpha we choose to be 90%. The constraint 6 is added and modifies our classical problem 4. We apply several transformations, and we express the maximum number of cars in a given section of the network as a function of mean value and standard deviations of the traffic flows. This expression is the z-score value of normalized stochastic function with a normal distribution, and this value is given from predefined, pre-calculated tables. In that manner, the mean value and the standard deviation represent functions of our variables x and u, green light duration, and the number of cars in the queue length. We choose two steps for estimations, for t0 and for t equal to 1, and in that manner we determine the mean value and the standard deviation for all sections of the network. This is the 13 inequality, which represent the goal function of our model, and it reflects the stochastic behavior of the traffic, where the values of initial number of vehicles, incoming vehicles, and maximum value are parameters in our model. X maximum and alpha are constants. And the value of alpha is chosen subjectively by the control engineer to prevent conjecture. This problem, stochastic optimization problem, is called SP. It is formalized as minimization of these parts of each section of the network with argument green light durations, where this problem is formalized again as a linear quadratic optimization problem with a number of constraints, where the matrices QP and RP are derived analytically according to the relation 30. In these both problems, deterministic and stochastic problem, we have arguments number of vehicles and green light duration, while the traffic light cycle is a fixed parameter. Our goal is to introduce more control variables in order to improve this complex object like the network. transport network, and that is why we introduce a second control variable. This is the traffic light cycle duration. For this reason, we propose hierarchical B-level optimization method, which extends the set of control variables and allows to achieve more goals in control process and accordingly satisfy more constraints. These optimization problems are not given in explicit analytical form and cannot be solved separately. This is the reason for using the B-level approach. Both the upper and lower problems have mutual interaction because the solution of the upper and lower level are interconnected. And this B-level problem is given in this form where U is the green light duration. We want this green light duration in all traffic lights of the network to be minimized, satisfying a number of constraints where the cycle is a solution of the upper level problem, where it is a gain optimization problem, where the green light duration is given here as solution from the lower level. Simulation. Here on this figure are the control cycles, which here is about 20 control cycles, and this is the number of queues of X3, the third queue length. It is related with the neighbor crossroad. The solution of the deterministic problem is in black, but it is the same as the stochastic problem in red. The solution of B-level problem is in blue, and it gives better results. About QLAN X14, the situation is nearly the same. Here you can see a little bit different values of deterministic and stochastic problem. The next example is of X16, where the B-level solution again is better. And the sum of all queues in the network is given in this picture, where again the B-level solution, which is the result of all queues in the network, gives better results. In conclusion, 3 formal models for urban traffic management are developed. The first model is on the base of nonlinear quadratic optimization problem that minimizes the number of vehicles in queues. The second optimization problem has an objective function that formalizes capacity constraints with probabilistic inequalities, and this model reflects the stochastic behavior of the traffic. The third optimization model is on the base of B-level hierarchical approach. It optimizes simultaneously 2 objective functions, minimizing the green light durations and cycles in the all crossroads of the network. The optimization problems for the 2 hierarchical levels are given. The models are numerically simulated and tested with traffic data from the Sofia region, and the solutions of the 3 optimization problems are compared and the results are presented graphically. The comparison gives preferences to the B-level results. The simulation shows significant reduction in the total length of queues into our urban network when we apply B-level optimizations. Another positive result is that the rapid convergence to the steady state on 6 iterations allows this approach to be applied in real time. And this research is funded by Bulgarian Research Fund. Thank you for your attention.